Good evening and welcome everyone to SecTalks Sydney 56, brought to you live on YouTube at our new temporary home. Thank you everyone for joining in. We've got a really exciting workshop today, led by our founder, Pedram. But before that, I'm just going to give a quick introduction to what SecTalks is for anyone new, especially those who are remote from Sydney and usually don't attend our events. SecTalks is a monthly or bi-monthly information security meetup hosted in Sydney, typically at a venue supplied by one of our sponsors. But obviously, for now, we're running these remotely live on YouTube. So thanks everyone for bearing with us for how we adapt to the situation and continue to bring you events. So as you know, it's a non-profit independent meetup that is run by community members, and we encourage the community to get involved in the presentations and the talks and the challenges that we have. There's no vendor talks or sales pitches. And we'd like to thank our sponsors as usual, PwC, Google, SecDim, and Atlassian. So thanks to all our sponsors. If you'd like to get involved, you can fill out our call for papers or our call for CTF. If you'd like to sponsor SecTalks Sydney, you can reach us at sydney@sectalks.org. That's also the email to get into an invite into our Slack channel as well. Typically, we would have a networking session, but but for now, you can join us in our Slack channel. Again, email sectalks@sydney.org, sydney@sectalks.org for an invite to our Slack channel. And that brings us to the presentation for tonight, which is a secure coding workshop. It's led by Pedram. He is a founder of SecTalks, and we're very excited to have Pedram deliver this workshop. If you're haven't already prepared, if you have a look at the meetup group, you can see what requirements you'll have to participate. But again, you can just watch the stream as well if you don't want to be involved in the practical. So there's going to be two parts. There's going to be the first part, which is just theory. You can just watch it. And secondly, you can actually participate if you have the correct setup already. I'm going to hand it over to Pedram, who will take it away.
Yeah, thanks. Thanks, Craig, and good evening, everyone. Well, the original idea was to run these sessions in person, well, in our usual venue. But given the time and the restrictions, let's see how it will go online. The workshop is quite interactive, and I may ask some questions or may ask for your comments. So please use either the YouTube live chat, or if you are part of the Slack group, please use the SecTalks Sydney Slack channel. And so that will also help me to how to gauge the content of the workshop. Now, this workshop is obviously for people more with the software engineering, software architecture, software design background. However, if as part of your role, you are doing any secure code review or any white box type assessment, you will find these workshops also relevant, and I hope it will be useful for you. This will be the first workshop, which the idea of these workshops, as I talked about it last year, is to talk about a little bit more about the defender side of the game and not so much about how to break stuff. This is a time we want to put the sleeves off and talk about how we can fix some of these issues. We understand some of the, well, some or many of the problems when it comes to fixing a security bug, and hopefully we can touch on some of those. I selected numeric overflow as our first topic because I found these security bugs is quite common in many programming languages and many programs out there. Let me start by giving you a bit of background that where the story starts. So as you may have known or been to any computer science type course, you know the CPUs, they have tiny part of the memory. Well, they have tiny memories called registers. And these registers are traditionally, has been used for arithmetic operation, pluses, minus, multiplication, and so forth. And like any type of the memory, the size of this memory is limited. And in a 64-bit, a common processors in most modern computers, we have obviously 64-bit available in our registers, which can be used to store a value up to 2 power 64 minus 1. In a 32-bit register, we can store a value up to 2 power 32 minus 1, which is equivalent of the number you can see at the last bullet point. In a 32-bit register, we can store a number which is the most significant digit is 4, following with 9 other digits. In a 64-bit system, we can store a number, a 20-digit number starting with the most significant digit of 1. Okay, having that in mind, having those numbers in mind, what do you think will be the result of this small code snippet, this pseudo code? Whatever comes to your mind, you can feel free to push it as a comment or in the Slack channel. So, do you think the program will crash, the computer will shut down? What will really happen once that total fee number will reach to that function make transaction? What will be the value in total fee? Would be at that number, that large number, plus 1, 2, 3, 4, would be something less, would be something more. The software will just throw an exception? Any thoughts, ideas? So it will turn to this massive negative number. Well, effectively, if that was a code for suppose an accounting system, we may end up refunding the user when we are calculating the total fee, because the number ends up being a massive negative number. Now, the questions you may ask, this number that you can see here is way lower than this number here for the 32-bit system, or even 64-bit, way lower than 64-bit system. So why you may think the software may crash or may result to this value? Well, as you could guess, and that is the title of this slide, this is to do with numeric overflow. But let's just dive a little bit deeper and understand what actually happened behind the scene. The reason for this behavior is two reasons, two issues. One is that commonly the integer types are stored as fixed point format. And fixed point format means we are using fixed number of bits to store this. And this fixed number of bits is relative to the processor architecture. So a 32-bit processor will only have 32-bit available for the integer, and 64-bit, 64 digits. Okay, that makes sense. But why again, this number is the original value that we had right there was a lot lower than this big number here. And this is to do with giving that limited memory size that we have. We want to store both negative numbers and positive numbers. So effectively, we have half of that space available for us. The number that you see in the example was effectively that positive, the maximum positive number in the range, plus 100, plus 1,000, 1, 2, 3, 4. I just want to bring you to this fact that the negative number, the least significant digit is 8 in the 32-bit system, but for the positive numbers is 7. I often find people may think the maximum or minimum range are both these positive number, which ends with the least significant bit of 7. Now, okay, that makes sense. All right, so the CPU or the register will reach the maximum number that it can store. And the first bit is used, as I mentioned, to signal whether the number is positive or negative. There's one other thing happens, and that is to do with the way that our microprocessors are implemented. And they are, once the value is reached to then beyond the range that they can represent or hold, they will use what is known as a modulus arithmetic. I will get back to the modulus arithmetic later, but just let's explore the issue again. If a given value is bigger or smaller than a numeric range that our CPU or the registers they can hold, the value will wrap around. And suddenly it turns to a negative or positive number, respectively. So what about that modulus arithmetic? Well, we actually use modulus arithmetic in our daily life quite a lot. Suppose you go to a doctor and she will prescribe a medicine that I need to take every 4 hours. If suppose that now is 9 p.m., well, we immediately know that the next time that I need to take this medicine is, in fact, 1 a.m. Behind the scene, we did use modulus arithmetic to come up with this 1 a.m. So what we actually did, the 9 p.m. equivalent 21 plus 6 is 27. Well, we don't have 27 hours. We know that 27 is bigger than 24. Well, that's the overflow condition happening in our brain. And we automatically handle this situation by dividing 27 by 24, which a reminder of that will be 3. So it will be 1, and that will be the 1 a.m. that we know. So this modulus arithmetic makes perfect sense in the context of time. It may not make sense in many other contexts, as you can see in the example that I had in the previous slides. That number that we saw that was added as a fee, when you plus that with 1, 2, 3, 4, it come up with this bigger number here. And this number is bigger than what a 32-bit register can hold. This number will be divided by 2 power 31. And then we're gonna get this number 1233. And I'm not gonna go to the detail of how the negative numbers is represented, but this number here is effectively this massive minus negative number. And that's how we come up with this big number when we did that arithmetic. So what is the danger of this issue as you expect? Well, we are adding 2 positive numbers and suddenly it can turn to negative, and that can easily impact the data integrity and availability of our program. So now, do you think whatever I'm talking are science fiction? It never happened in the real world? Well, not really. It happened quite a lot. You may be surprised to hear that the first time when this issue happened, well, not really. The first time of one of the common examples is actually to do with this, one of the all-time favorite game called Pac-Man. If you were a gamer back in the days, you know that in Pac-Man, it was impossible to pass level 256, which was the final level. So effectively, once the player was reaching the final level, and what will happen is, this is level 255. When you reach to the next level, what you could see on the half of the screen are all those gibberish random numbers and characters. And effectively, nobody could pass, or maybe some player managed to pass it. I don't know, but that was effectively you could get. And the reason behind this issue was the internal level counter, which was set to 255, and that is the level 256, starting with 0. When the routine that was called to draw the level numbers, and again, if you recall, the Pac-Man had some fruits and like things on the bottom, which was representative of the level that the player was. When this routine was called to draw the fruits for the level 256, behind the scene, it was used 8-bit CPU register. And in 8-bit CPU register, we could handle all the numbers all the way to 255. So we have an overflow right here. But since that routine didn't really know about this, it will start filling up the screen with all those random colors and shapes. But in reality, those things that you see on the screen, they are not actually random. These were the parts of the memory that belongs to the Pac-Man process that was printed out. So effectively, we have a memory disclosure just because of this overflow that happens, and that routine that was there to read to draw things that were actually going and reading different parts of the memory and drawing on the screen. Well, this could sound fun, and but we have more serious incident that happened because of this bug, and that is to do with airlines. It was interesting. There was a news on April 2015, so around like 5 years ago. The FAA, or Federal Aviation Administration, they advised the airlines to please try to reboot your Boeing 787 if you haven't rebooted them for the onboard system, if you haven't rebooted them for almost 8 months. And you may be surprised at what was the cause. The cause was, once they did the testing, this is like the Boeing did the testing, they found out that the power control unit will overflow if the onboard system has been kept on for effectively 280 days. That is equivalent of 2 power 32 seconds, and that will cause the system to shut down, the power generated system to shut down, which you don't really want to happen if you are in the airplane. So behind the scene, we have a very basic bug that could cause, well, I would say some interesting or devastating type problems. And we actually see it in practice, in a real life, in a lot of places, that numeric overflow happens. If you have an odometer in the car, in the old cars, you can see overflow happens there, or some old petrol stations, they had numbers that they record how many liters this petrol station over the years have been pumped out of it, and you could see overflow may happen there in the odometer. So what is the numeric overflow? If we want to put everything together, is when an arithmetic operation resulting to a numeric value that is outside of the range for the represented value. Due to the fixed format type or modulus arithmetic, this value will wrap around. So if we have an example of a program that receive or define or use a primitive types, such as integer, and if it's being fed with a maximum number that it can handle, it can result into the overflow, or if it being entered with a minimum number that type can hold, that can result to effectively underflow, which is effectively the same thing. Which languages are affected by this? The majority of the programming languages, and that regardless of whether they are the type languages or the weakly type languages, they are effective. So things like Java, Kotlin, C#, C, C++, Go, they are affected. Well, if you are a Python and Ruby programmer, be happy, because Python and Ruby, they are not affected due to the fact that the language behind the scene does what is known as upcasting. So by the time the overflow happens, they will cast the type to a bigger type or bigger integer to hold the value. In terms of JavaScript, the normal default type in a JavaScript, which is a number type, is not affected by numeric overflow. However, if we are using any type arrays, it is affected. One thing regarding to the JavaScript is the default number type is affected by another, maybe relatively serious security bug, which hopefully in some future workshops I will talk about it. So that was pretty much what I wanted to talk about numeric overflow. If you have any questions, any comments, you can put it in the comments or in the Slack channel so I can answer, because after this, we want to move to the practical part, and we're going to talk about the labs and 2 labs that I have selected for here. If you have any questions, feel free to ask now. Otherwise, meanwhile, I can show you the link to the lab. So if you want to do the lab, and it's again optional, but I highly encourage you to participate. These are the 2 links. I have 2 example applications or programs that we're going to use it. One is written in Java, the other one is in JavaScript. So go to gitlab.com/secteam/lab/java/numeric overflow. For JavaScript, same thing, but just replace Java with JS. What you want to do is log into the GitLab, fork this repository, and clone your forked repository offline. There is a README file. Only attempt to do the task 0 in that README file. And we are going to have maybe 5 or a bit more than 5-minute break, pause, and we will be back for the second part of this workshop. But if you have any questions, please feel free to ask now. Okay. I hope you managed to at least clone the repository and run the application. I will go through it again as part of this section. Now, we talked about Numeric Overflow. Now we want to look at the two example applications that we have. And the first thing we want to do, we want to see how we can catch this bug if we are reviewing a code, or we want to write a code and we want to avoid doing it. So the first thing is, this bug is quite simple to identify. Depending on the language that you have, you want to first list and identify all the primitive number parameters. Specifically, integer and long are in majority of the programming languages are used with a fixed type format. And the second thing we want to check is if these two values are being fed from an untrusted source. So if a user and attacker will be able to enter a massively large number for one of these types, or alternatively, is there any arithmetic operation done at some part in the code and that could potentially result to overflow or underflow? So as I said, it's relatively easy to find. Now, let me just give you an idea how we can do this in our program. So the first project that we have, I will first talk about the Java part. So this is the structure of the program. If you just go all the way and open the main.java file, well, it started with some boilerplate code and following with the main. Nothing quite specific here. We can see it's at line 19. It will call this method called approval. And if you look at the definition of the method approval, the first thing, well, it says it will check if a given amount, there's a typo there, if it is given amount is require approval, return true if a given amount is bigger than a given threshold. And where does the threshold is defined is right up here. 1,000, it is using a primitive type integer. And there's also a surcharge, which we will later see where it's being used. So we already identified two primitive types on line 8 and 9, and on line 34, there is actual amount value. So this method is getting a value as a string, and later on we'll parse this string value to an integer using parseInt and add that surcharge. Suppose this is a method that will calculate a surcharge for a given value. And right here, it will check if this is bigger than a threshold, it will return true, otherwise it will return false. Let me see if I can make this text a bit bigger, because some people seem to have issues viewing it. I hope this is better. So this is okay, let's just keep these three things in 3 lines in mind. So line 33, and this is highly likely where the issue can happen. Okay. Now, I'm not running the program for now. We want to go through this step by step. Let me move to the JavaScript example that we had. Again, this is a program folder architecture. If you open up the source folder, app.js, all the way from top, there are just some generic code that sets up our program. And yeah, it's an Express.js type application, nothing really interesting here. Right here, it will start the mapping part, where it will handle a GET request coming to the root of these hosts. And following that, it will pass 2 parameters, require, and then finally the response. The request, this is effectively the request, HTTP request that coming from the user. And over here, it will point to the request.query.amount right before passing it to the method approval. It will do one parseInt right here. You keep that in mind, line 22. Now let's look at the definition of the approval. Similarly to the Java example, we have an amount, which is if it is less than a threshold, then the approval is not required. So what we are having, again, we have the same threshold, we have the surcharge, and then we have this amount variable, which is using that typed array that I mentioned before. And what's happening over here is it will get that value, which comes from that HTTP request, and it will add the surcharge to that, and later on it will parse it to int, and we'll store it as one of the first item in that amount typed integer array that we have. And we are using, as you can expect, a 32-bit array to store this variable. Okay, so this part of the code could be interesting for us to investigate. I will maybe later on come back to this and ask that, do you think we may also have an overflow here on the line 22? But we should definitely have an overflow condition that's happening right here. Okay, now with that in mind, what I want to do is I want to go ahead and run our Java application just to see how it works. So if you have just cloned this repository, the first thing, well, all these instructions that I am talking about, you can find it in the README file. And if you look at the task 0, it takes you through all the things that you need to do to run the application, test it, and so forth. So the first thing, I've already done make build, so the program is already built. I do make run to just run this program just to see how it looks like. It is asking an amount from me. So if I just enter something like 100, it says the amount does not equal, and it will return as expected. Moving to my JavaScript application, sorry. If I run this program, then it's gonna run an Express Node.js application for me, and later on I can start port 8080. So I can send a GET request to this and specify a query parameter amount. And hopefully that will give me some return. So 100 does not require approval as expected. Now if I enter something more than that, let's say 10,000, it will say I get 10,000 requires approval. If I look at the logs for this application, you can see these are pretty effectively those amount number once the surcharge has been added to it. Okay, so one more thing you want to have a look here is for every program, we do have some unit tests that are within the test directory. So, and these unit tests are divided as usability unit tests, which are common unit tests that you may find in every program that test the functionality of the code that we have written. So in our usability test, we are testing for, well, if we are expecting that 990 does not require approval, sorry, needs approval, but 500 does not need approval. This is due to the fact that we are adding surcharge here and that it is higher than a threshold. To run the unit test, you can just simply write make test. I'm not doing it here. But also we have security unit tests, which are testing for those edge cases that we talked today. For example, this one here is giving that integer parameter the maximum number, and the expected result here, if we want to pass this test, we expect the program should throw a illegal argument exception. But in this other example, we are testing for the underflow, this number, and we are expecting the program to throw illegal argument exception, or any other exception that you want to define. But the whole idea here is just to see this test. Now to run these security unit tests, you can just simply type in make security test, and that will just do it now on your own, and that will throw in some errors, which we will get back to them a bit later. For our JavaScript code, the story is similar. Inside the test directory, we have two sets of tests: app.test.js, typical unit, common to unit test, and appsecurity.test.js, which is our security unit test. If I look at the app.test, here I'm expecting that for amount of 500, I need to receive 200. For 101, I expect to receive 400. And this is just a health check of the whole program, whether it runs or not. So these are my unit tests, and my security unit tests are quite different. So I'm testing for quite a few things here. I'm ignoring the first one for now. If you look at these tests right here, the first test, what it does is it checks for the maximum amount that can be stored in the type array in 32-bit and expect to receive the range error exception. And this is that number here. The other one, it will check for some arithmetic results of taking out that surcharge out of that maximum number and later on add ones to it. So that will create overflow and expect to receive again, a range error exception. And I'm doing the same thing with the underflow condition. So a minor integer negative number minus 10, that will brings me to the integer mean value, minus 1 cause to overflow. And the first test, well, this is just given the context of the program. If this was a program that will deal with the currencies and money, well, we should not expect to receive a negative number anyway. So this is a test for that. So effectively what we want to do is we want to go back to our application later on, and we want to fix it. So once I run security test later, this security test will pass. And this is also to do with my Java program. Once we patch this program later on, we come back here, we run next security test, and this will pass. I don't want to run it for now because I want to move to the next part. So I talked about static analysis. It was quite easy to identify this type of part. The next part is how you can find this at runtime. Again, relatively, numeric overflow is quite easy to discover. As some of you most likely have guessed, we identify those numeric parameters to the program, and we play with the values that are either higher than a maximum range or lower than the range. Here is a list of some interesting numbers that, if you are fuzzing an application, if you want to test it, or if you want to create a unit test, these numbers could be quite useful for you. Starting from integer max plus 1, integer minimum minus 1, and the other values are for a 64-bit system. And this final value that you can see here, well, later on, this is to do with that IEEE 754 number formats, which some programs are using it to represent their values. So for our case, these numbers are interesting. I will just grab one of them. And if I go back to my Java program, run the program, I'm giving it this number, which is the integer max. And well, the amount, as you can see, overflow happened, and the return is the amount does not require an approval. We just go try the other test input. Just do it with let's try this. It does not require approval. Let's try the same thing with our JavaScript program. So this, what you can see, is a result of that security unit test that I ran. And as you can see, all the security unit tests failed as expected. Let's just run the program and see how it behaves when I giving those test inputs. The server is listening. Let's go to our specific client and give it our integer max value, and let's see what will happen here. So does not require approval. If I go back here, you can see the number that actually received by the application or processed was this maximum, this big negative number. So maybe you can give it a try for a couple of minutes. Try all these test inputs, try run your application and see how the program behaves. Okay, so far we talked about how we can identify numeric overflow through code review and also runtime analysis. And these test inputs that I have put here, quite useful to use when you're revising the application, or if you want to create some security unit tests to test for these things in your program. It was quite a useful list to have. Now, the next part that I'm going to talk about is pretty much the juice of this workshop, is to how to avoid this bug, how to write an application that is not vulnerable to numeric overflow. Again, as some of you may have already guessed, one of the things that you may hear most of the security professionals will recommend is, hey, just to do input validation and make sure the value that you are received in your application is within your expected range. Now, I want to explore on this recommendation a bit more and be a bit more pragmatic and go to a bit of detail that what actually we mean by input validation, and specifically when we want to validate an untrusted data. So to do that, I just want to take one step back and talk about, in general, where can I address or a security issue or security bug in my program. And when it comes to the patching or fixing a security bug, there are many ways we can fix a bug. Security patches or security fixes, I like to think about them as like layers, effectively layers within a burger, a very tall burger. And depending on the program functionality, some of these layers are quite effective. And what are those layers that we can think about? Well, obviously, this list that I put here is not the exhaustive list of all the possible ways, but these are commonly different places that we can put a security patch. Obviously, some of them are more effective, depending on the type of a security bug that we are addressing. But if I want to ask you a question that which one of these layer or layers you think will be addressing the security bug that we just covered, which one of them you will pick? And I hope I can receive some answers or some comments on this. Which one of them you think is the best to address a given security issue that we talked about? Maybe a better question is to ask, how many layers your favorite burger you would like to have? Like, I believe nobody likes a burger just with the buns, or a burger just with buns and lettuce, right? I don't even call that a burger if something comes with the buns or lettuce. It is flavorless. Well, similarly to the security will be flavorless if we are only talking about a single layer. So the whole idea here is that the more layers that we have, the better when it comes to the security patching. Now, those highlighted layers that I have up there are effectively the focus of the talk that we are having right now. Now, then if we are focusing on a design and implementation, the way that we can address a security bug, what do you think a common approach is when we are addressing a bug? Well, the majority of cases, the programmer or the programming team will add an if clause or to their validation routine to address the bug. Well, unfortunately, although this is a common practice, I have seen again and again that over the time, this practice turned the program to the pile of patchwork. It just makes the program ugly. Just makes the code review quite a lot harder because of all these if clause patches. And a lot of times what I've seen is they need to add a lot of comments around each of these if clause patchwork just to explain why they are there. And honestly, any software engineer or trying to adopt a good software design, they would not like to see these if clause patches. The problem is to avoid that security bug. That is the way that most of the programmers they may try to do. The other common approach, which is being also advocated, that I've seen being used to address a security bug, is to patch the program against every possible vulnerability. And this is what I call a vulnerability-driven development, which is, again, is hard to maintain, and it is highly likely that some vulnerability will be missed or not addressed safely. The problem with these two practices, which is used, is we are shifting the focus on all the possible things that program should not do, which is a completely different mindset for any software engineer. It is like asking an engineer to build a car, but rather than be telling the engineer about the car that we're wishing to be built, we're telling her that, hey, make sure your car does not look like a bicycle, or it only has 2 wheels. It shouldn't have like 2 wheels like a motorbike. I don't know. It doesn't require a track to run, and it shouldn't have a jet engine like an airplane. I'm sure there is no engineer out there that would be able to build the car, giving the car a specification. And that is pretty much from software engineer perspective, the spec that we are giving to some programmers to patch the security bugs, which here we are with a lot of vulnerable programs, or as Dr. Gottman puts it better, that a great many of today's security technologies are secure only because no one has ever bothered attacking them. This is a quote in the start of his book called Engineering Security. So what I believe is we cannot ask to build a program by focusing on all the 100,000 vulnerabilities that can go wrong, that can make the program to behave differently. But if we are saying this approach may not be effective, is there any other way, is there any other approach that helps our programmers to focus on a good design software, but at the same time, it can address security issues? Well, there are some ideas that is being floating around, not quite recently, but for a long time, and which I personally find it very interesting. And one of them is to do with the whole approach of defensive programming, which the idea is quite simple, which talks about, it is an approach that plans for contingencies or those unforeseen errors in the design and implementation stage of the program. This defensive programming has been used to build quite a lot of safety critical programs. And apart from security, this approach also considers things like high availability or the safety issues that may matter for some programs. But again, it is not a new thing. And interestingly enough, defensive designs or defensive architectures has been around in other industries for quite a long time. For example, in the design of the power wall sockets with different amps, this design of this wall socket enforces only plugging appliances with equal or less current rating. And so we can imagine that in the design of this program, there was a defensive design idea behind it to reduce the risk of power overload. So if I have appliances, the appliance that, I don't know, needs 20 amp to run, if I connect it to wrongly to a wall socket that only puts out 10 amps, that is cause of, it can cause power overload, which either is gonna, the electric circuit gonna short circuit, or high likely we're gonna have some fire issues. So the idea of this defensive programming is similar to this. And my work is to take some of these already established security principles or design patterns that is out there and find their applications in our modern programs. Rather than we focus on the vulnerabilities only to fix a bug, we focus on how we can adopt these design patterns or principles to build a more secure program. And the idea behind these design patterns are to make the program to handle the complexity of some of these security vulnerabilities a lot better, and more importantly, make these security patches maintainable. The whole idea of some of these principles are to bring back the security issues that happens at runtime, or put in a technical term, security bugs effectively is a runtime exception that happens when the program runs. We want to program in a way that we are able to detect, identify, and patch these bugs during the dev time. So that is the whole concept around early errors. And we will see a lot of times that some of these principles, if they are followed properly, they implicitly will address a number of security issues, regardless if the programming team were aware of all the flavor of this type of security bug. So this is obviously a big objective that defensive programming has. However, this is the idea that it tries to speak a builder mindset rather than a breaker mindset. And it tries to encourage people to follow some good practices to design a better software that they can be proud of, rather than a software that goes to the prod and later on they need to come back to put all sorts of ugly if-clause patches to just make the program more secure. I don't know, maybe in a future workshops, we will also explore some of the patches that was introduced for the vulnerabilities with the logos and names. And as we explore them, you will find out that this is also another example of what I call it like an ugly patch, an if-clause patch that was just thrown in just to say, okay, we are fixed against these bugs. And the program inherently is not designed and that is not robust enough a future type attack that may happen just due to that bug. So with that, obviously I have collected a number of these principles, but for the sake of our talk today, I'm going to talk about the first one, which is one of the core principles in defensive programming. Regardless of what programs that we have, this is a principle that we want to follow, and that is to do with validating the data. And I'm sure most of you have heard about data validation. We need to validate the untrusted data, but again, we want to look at this in more detail to see what actually we mean by that. So by far, all sort of injection attacks, different vulnerability at the client side, at the server side happens just due to the fact that we are trusting an untrusted data, and untrusted data gets away in our program without sufficient validation, and that's the root cause of the issue. A lot of times we will see that a lot of programs, they only assume the untrusted data or the data that comes from the user. But unfortunately, that is not the case today, where our program could be a service within the MSA architecture, and it receive and respond to a number of events that happen. And those events may come from other microservices, or it could be a response from a third-party provider that our program is depending on. These are all a sample subset of untrusted data that they can find its way in our program. Now, the principle, the idea behind this, the first principle is about this very nicely put quote by Michael Howard in his book, Writing Secure Code, that just remember, all input are evil, or input is evil until proven otherwise. So here we are saying that anytime we have a data that cross the boundary between untrusted and trusted environment, that must be validated regardless. So there are two letters here that I have highlighted. I will try to explore the first one first, and then later on, if there was time, we'll talk about what I mean by untrusted. Now, the first thing is when it comes to the validation, and I quite like to get your attention here, because this is something that I have seen again and again. When we're talking about input validation, I open the code, and what I can see is that the team just put a regex there or a regular expression pattern, and they think that it will work and will fix the problem. There was an interesting quote that I read somewhere that people try to fix their program, the security bugs, by writing a regular expression, but now they have two problems because they have written a regular expression, and that is also a complex things to handle. Now, this is not, I'm not talking about putting regular expression aside. Definitely, we're going to use it when we are doing a specific type of validation. But remember, regular expression are one of the many things that we need to do when it comes to the validation. And here, what I want to talk is what data properties that should be validated. These are the 5 data properties that, regardless of what data is coming to a program, we need to make sure we are validating before starting using that data. And I have an acronym called SLIS, just to remember all these, which is acronym for E for emptiness, S for size, L for lexical, Y for syntax, and S for semantic. For the purpose of this talk, I just don't want to make this presentation too long. I'm only going to focus on the first 2. And as I am going through, these are the things effectively I hope you will borrow and will apply in those JavaScript and Java programs that were given to you. So starting with first, which talks about emptiness, and some of them may sound very, very trivial or very easy to do, but interestingly enough, a lot of programs, they just don't do it. And this is one example that I have here. In this sample pseudocode that, well, it looks like a Java code, it's supposed to be a pseudocode. Imagine what the program is trying to do. It tries to read an environment variable and put that environment variable to the variable called key. And later on, we'll use that key to initialize some sort of encryption algorithm. Now, the assumptions right here we have is that we did never assume here that the key may not be even available as an environment variable. And if it doesn't exist, it will return null. And this is the cause of what is known as a null point exception. Or in some programming languages, it may silently, the program may continue when the result is null, and that encryption algorithm may initialize with no key. That means a weak encryption setup. Or in languages like C, it may segfault. In Java, that is a $1 million problem, which is known as a null point exception. It really depends. And this is to do with, we are not checking for emptiness. So that is regardless of the program that you're working on, the first and foremost, check if the data that you are expecting is given to your method. As simple as that. As I said, different programming languages, they behave differently when it comes to null type, none, or like different types when the value is not provided. So we want to first check if the data is given. Otherwise, we want to throw exception and do not continue handling the request. With the last 2 options that I got, not a number and undefined, this is so far are specific to JavaScript. So if you're a JavaScript developer, if you're dealing with a number, these are the other 2 checks that you want to do. Also check that if the given value is not a number, or none, or if it is undefined. Undefined is to do with a variable which is defined but is not initialized. So on top of null check, you want to make sure that you also check for not a number or undefined. So this could be a sample pseudocode. So if I want to, suppose I have a program that expects the ISBN number, the international standard book number. And the first validation is simple. Is this value not null? If it is not null, I will continue the rest of the program. Cool. Now, the second property that I wanted to talk is to do with size. And it's an example that I have here. Suppose I have this program, this method in my program that will, let's say it's like a shopping cart, and it will try to extract the order quantity, the quantity of the order that the customer puts in. It's a HTTP request that comes to the application. The first thing it does is it will check if the quantity field exists in the request. If so, it will parse that as an integer and return. Otherwise, it will throw quantity not found exception. So by the looks of it, the application does check for the emptiness right here. However, there is something else can go wrong. what if the quantity that is provided by the user here is 0? Or what if the quantity is negative? Or what if the quantity is very large? And by very large, I mean like 2 power 30 digits. And that is equivalent of 2 gigabytes of data. Do you think the program will go out of the memory or will crash? Or is this an expected size that the program should happen? Or is the attacker can enter this much of data? The short answer is yes, they can. We will come back to it, that why. But obviously, regardless of whether they can do it or not, this size of the data is completely unexpected. And the reason we are open to these type of issues is because our program does not do size validation, which is the second property that I wanted to talk. What range of data is acceptable by your program? Simple as check for the length. This is a 10 character, this is a 10 digit. What is the minimum number? What is the maximum length? What is the maximum number or maximum length? Or minimum number or minimum length? It's a quick check, it's a beautiful check. It will prevent abnormal data into the program, which we don't necessarily need to load this huge chunk of memory in this data in the memory, and which may require unnecessary heavy processing. And first and foremost, we don't want to put it to the regular expression just for do this simple length check. Now, our example just improved here. Again, for ISBN, it's a known format. And once we did the null check, the second thing we want to check if it contains between 10 to 13 characters, which is the standard format right here. Now, regardless of if the programmer knew about numeric overflow, by just doing the emptiness check and the size check, I hope you agree with me that we have already addressed the numeric overflow issue just right here. Just one thing to remember, when it comes to the size validation, you want to think about applying the size validation both at field and protocol level, because a lot of protocols that we are using, they unfortunately do not specify the size limit. And now I'm coming back to the example that I have given. For example, in the HTTP request, the RFC 2616 does not define the specific size limit. So a user is able to create a post request, and a post body can be any size. Now, in practice, this is a bit different. So specifically for post request, it depending on a web server, and it ranges between, if we are, for example, using Nginx or Apache or IIS, it can range the default value. It ranges between 1 megabyte to 2 gigabyte. It really depends what is in our infrastructure. When it comes to the GET request, again, the de facto limit, again, is not a standard, which is enforced by the URL length limit is 2 kilobyte. Although in the amendment that they have done to the RFC, they limit that to 8 kilobyte octet. But in practice, the majority of the programs, they only expect up to 2 kilobytes. But again, I don't really think in the majority of programs, we really expect to see that size of the GET request. One thing just to remember, the HTTP clients, like the browsers, they do enforce some restriction on both post and GET. But again, this is a client-side protection. We do not want to rely on it. And lastly, the header content length that is within the HTTP request, that we can use it to see what is the size of the post body. Just remember that is again user controllable. It is untrusted and can be tampered. So we want to think about a different way when we want to apply a size check on the protocol level. I have seen examples of just one idea. I've seen they have created a stream buffer and they just read the buffer up until the point that they expect, and then they stopped. This was one of the way they tried to stop to limit the size on the protocol. The other thing was they kind of delegate this protocol size check to the web server, and they just did it in the configuration of the web server. Finally, just reiterate this, please avoid use regular expression for size validation. Your programming language has a nice API methods, length, whatever, that can does the length check, and it is a lot faster, and it is a lot more, performance is a lot better. So that was pretty much what I wanted to talk about, how we can address this bug, so untrusted data validation. Now, I hope you got some ideas how you can go back and fix the issue. I'm just worried about the time. It's quite like 7:15 already. One thing you can do is, if you have any questions or thoughts, I will be available on chat and Slack everywhere, that if you guys have any questions regarding to this. In the repositories, maybe I can bring it up here. There is a branch called patch, and if you browse to that, you can see a sample patch for the given lab. And but my suggestion is, for example, this is for the JavaScript part, that how the validation is being defined. But my suggestion is, try to think about both emptiness and size, and just do it on your own. Apply the patch to the program and run both the usability test, make test, or the security unit test, and make sure your program pass both these tests. Once you are happy, you can just git push, and there is an automated build process there that if you have done everything correctly, it will pass the build, and you will be all happy. I want just some concluding thoughts now to wrap this up. Go back to the, where do I have the, I'll go back to the previous slide. So how to avoid this bug? Well, I talked about one of the principles. Technically, untrusted data validation principle does address this bug. Technically, however, well, when it is to do with the simple programs or these lab programs, it's perfect, apply it there and fix the issue. However, if you're working in an enterprise environment, if you're working in more complex programs, this needs to be improved. And this is effectively a subtopic of the other ideas and principles that I have here, which deal with those complexity when the program is large and you want to make sure your patch is maintainable and can grow over time. Cool. So that was all. One last thing to remember is, which was quite interesting for me, GPUs. And we talked about CPU and the modulus arithmetic. GPUs turn out to be using an algorithm called saturation algorithm. And the idea behind this algorithm is, once the value reaches to the range that they can hold, it will clamp. Because effectively, once the int is max number, it will fix at that point. Or when there's the integer min number, it will actually fix and clamp to that point. So we don't really get the overflow problems when it comes to the GPUs. Now, I just leave you with this question, that why do you think CPUs did not implement it? Well, the common microprocessors, they don't implement these saturation algorithms. So hopefully all the problem with the numeric will be solved. That was all I wanted to talk today. I hope you guys enjoyed. You can find me on Slack and Twitter. If you want, you can send me an email. And I will be online for a couple of minutes if you have any questions that you would like me to go through during this live channel we have.
Awesome, thanks, Pedram. If anyone had any questions, just post them in the YouTube channel or in the Slack group.
I think we can't hear you.
Can you hear me now?
No. Cool. Thanks, everyone. Just we can't hear Craig, but thanks, everyone. Yeah, hopefully we will see you at the next session.